Hello and welcome to lesson 14, how earthquakes affect landforms and landscapes. Now have a look at the screen and you'll see that this is looking at 3A4, the effects earthquakes have on landforms and landscapes, including the development of escarpments and rift valleys. And this lesson is going to tackle this head on. So first of all then, we're looking at the landforms and landscapes at terrestrial divergent margins. Now remember that divergent is where the lithosphere is being pulled apart. We're talking about terrestrial and we're talking about land-based terrestrial. So these are quite rare because most divergent margins occur underwater as seafloor spreading ridges. The two exceptions on Earth are in Iceland and East Africa, where earthquakes cause the development of landforms, such as escarpments, and landscapes dominated by rift valleys. So this idea of landforms, remember landforms are small features, individual landscape features, individual elements, physical elements of a landscape. And remember the landscape from GCSE Geography, landscape is the visual features of the surface features. So a landform itself, things like a cliff, landforms, things like a stack, a beach, a bay, headland, all those things are individual pieces, components. And when you put all those landforms together, you then form landscapes. So landforms is the small feature, and when you put those together, you get what's called a landform assemblage. You get lots of landforms that fit together or in a sort of place context. And when you put them all together, you get a landscape. So landforms is small scale, landscapes is larger scale. So here's a picture of what's happening. And this is the latest science behind what's happening with plate tectonics. Text here is talking about the tensional stress, where the lithosphere has been pulled apart. Now here you can see the crust is being stretched, it's thinning, and there are cracks forming. The cracks are formed as steep angle, almost vertical, fault planes. And here you can see these cracks forming here. So we're looking really at the idea of this first landform. The first landform is escarpments. How do they form? They're clearly formed by earthquakes, and this is going to show you how. So first of all, we have a normal fault. Now, we looked at this before. A normal fault is where you've got, again, quite a steep angle fault plane, and these are two lithospheric blocks. And I guess this really is shear stress. Shear stress is where you've got forces parallel to the fault plane. So, and remember, friction causes these blocks to be stuck together, and all the time the stress is increasing, the shear stress is increasing, friction is holding it in place. There's going to be some bending happening, there's going to be that shear strain happening, and finally there's going to be the fracture. And when that fracture happens, all that shear stress energy that had been building up and accumulating for a long time, maybe tens of years, maybe centuries, maybe even millennia, is suddenly released in a few seconds or even up to a minute, causing those violent seismic waves which radiate out like ripples on a pond. And during the earthquake, one of these blocks is going to go up and one is going to go down. Well, I'll show you on the next picture anyway, because that side, there was a new area exposed. It was a very light bit here. This might start again. And that bit was the fault scarp, which in our spec is called an escarpment. So an escarpment is a smooth, steep, cliff-like rock face formed at a normal fault. It's not happy here. It's quite a large file. I'm asking the computer to do a lot of processing. But that smooth surface is called a fault plane. We'll see that on the next slide. Oh, here it is. So this bit here, that is the escarpment. That's the escarpment. See the escarpment forming? So these can form within seconds. There could be flat land. And suddenly when the earthquake happens, within 10, 20, 30, 40, 50, 60 seconds, a cliff can suddenly emerge out of the ground. And that is called an escarpment. Geologists also call it a fault scarp. Okay. So in antiquity, in ancient history, in ancient Greece, escarpments, fault scarps, were used to help build places of worship. Here is the fault scarp. So during an earthquake, this cliff and land sort of rose up out of the ground, forming this cliff. You can see here that it was used as the back wall for the temple of Hera Acrae, whatever that is. Nice bit of coastal geography here. There's a nice wave cut notch happening down here as well, due to the micro tidal range in the Mediterranean. But that's for another story. So the escarpment is literally the other side of that little bit down there. Here's another lovely example of an escarpment, and this is really quite a spectacular high cliff. This could be about 200 or 300 meters, and remember, this arose in the course of 30 seconds, 1 minute, a violent earthquake, which would have actually been very hazardous for local people. That smooth surface there is actually the fault plane, which you can see, and it's quite an old feature now, so it's been slowly eroded and weathered, mostly weathered actually here, so it's got some cracks and joints which have been eaten away by weathering. And this escarpment is at a place called Cnidus in Turkey, used as the back wall for the temple of Demeter. Right, rewind it, but I can't now. So hopefully you should be able to see this. Should put this on a loop, but next time. Just you could fast forward this bit, can't you? There we are. As see, one block slips down, and you've got two fault scarps there, two escarpments, and you've got a nice rift valley in the middle, just here. There's the fault scarp, the escarpment, and here is the rift valley. So it goes escarpment, flat rift valley, escarpment, and then this is some sort of plateau going on here. Here's the normal fault. Here's the normal fault. These are three different blocks of the lithosphere, and the central one has come down. Normal faults, yes. So you've got one normal fault produces one escarpment, and the other normal fault produces a second escarpment. Here's a nice block diagram actually from East Africa. The reality, as with all things in geography, is much more complicated. And here I've got loads and loads of different escarpments. If you look, so one of their jobs is for you to count how many there are here. But there's one, there's two, there's three. You carry on counting. Interestingly here, because of the orientation of the fault planes, yes, you've got a rift valley here, but interestingly, you've also got a rift valley here as well. It's quite cool. And the central block, which hasn't sunk down because of its angle, because it can't slip down, the angles of the fault planes mean that it just stays there. This is called a horst, not a horse, a horst. And these bits here are rift valleys. And sometimes they're called graben, which I think is a German phrase. Why are lakes often found in rift valleys? Well, this part of East Africa gets high amounts of precipitation. There's lots of rivers. Rivers go downhill, and water collects in depressions in low areas. And so these lakes have basically been fed by rivers, and they're just huge, long features we'll see in a moment. Here's my map of the continent of Africa. I've got this idea that the lithosphere of East Africa is under tensional stress. It's being pulled apart. And the rift valleys, they start actually in Eritrea. In fact, it starts really up here in the Holy Land around Israel, Palestine. It goes down the Red Sea, and then this is the triple junction, which we learnt about before, where you've got three tectonic plates meeting. And this is therefore being pulled apart. So we have a rift valley going through Ethiopia. It's hard to see in some parts because of the highlands. And then down here it goes through Kenya, and then also it carries on going down here. You might be able to hear an ice cream van at the window. It carries on going down through here, and then it splits into two branches down here. So it's quite a complex geological feature in East Africa. In total, the Rift Valley is 4,000 kilometers long. You know, it's from here to, it's like from London to the middle part of America. It's very, very long. And the escarpments on either side of the Rift Valley can be almost, well, over 600 meters high. We're talking about really large landforms and huge landscape features that dominate the whole landscape and topography of East Africa. Well, here's a few maps from the atlas which I scanned in this afternoon. You can see all the countries. Obviously, this is a slightly old atlas map because Sudan, as you know, there's Sudan and South Sudan, with the border being somewhere along this river. Apart from that, it's still pretty good. So we're looking really in this area around here. We're looking from Ethiopia, Uganda, Tanzania, Malawi, right down into Mozambique. Here's a physical map which shows us the relief, shows us the shape of the land, shows us the terrain, shows us altitude, and shows us rivers as well. So here's the Rift Valley, comes down the Red Sea, triple junction over here somewhere, and then the Rift Valley comes down here. Now look carefully, can you see some long lakes? And those lakes have formed in the depression, the low part of the Rift Valley. This next map, I'm zooming into East Africa. And Lake Victoria is not in the Rift Valley. That's just a sort of sitting on a plateau where there's a slight bowing down of the crust and water collects there. But along here you can see the Rift Valley, and all these are lakes, and they're sitting in the Rift Valley. Here's Rwanda, Burundi. This country over here is the Democratic Republic of Congo. So where the Congolese and the Tanzania border meet, here is a lake called Lake Tanganyika, and this is a monstrously long Rift Valley lake. Carries on going down here. This is called Lake Nyasa. It used to be called Lake Malawi. I'm not sure actually, you can't read it, but you can see it on the PDFs. So we're talking about a huge landscape feature. And here is a beautiful, beautiful photograph of the edge of the Rift Valley in Kenya. And this is a very, very weathered fault scarp. Hang on a minute, must use the right language. OCR, escarpment. Here is a whopper of an escarpment. You can see really we're talking about more than 600 meters high, this escarpment. This is formed by earthquakes. So the whole landscape, remember this whole lesson is about how earthquakes create landscapes. And this entire fault scarp, escarpment, this entire escarpment has been formed by subsequent earthquake events. And this bit has literally been thrust up out of the lithosphere. Weathering and erosion slowly denude. This is a great word in geography. Denude is all about wearing away, wearing down, and it's basically a word that you use for talking about weathering and erosion together, working together to wear away the land, to wear it down. You've got a big mountain, it goes down, it gets lower down. And this process will take millennia. Okay, right, the second part of the lesson then is looking at convergent collision margins, where you get mountains forming. And here earthquakes again are at work to create huge landforms and huge landscapes. So at convergent collision margins, the continental lithosphere is placed under immense, huge compressional stress. Remember, stress is the force, and the movement was strain, but stress is the force. The lithosphere fractures, it cracks, creating low-angled, almost horizontal thrust faults. And if you look carefully, you can see these cracks here. These are low-angle thrust faulting, and here you've got one plate colliding with another one, and you've got high mountains being formed. Subcontinental collision. It suggests that subduction has happened here. In the past it did, but then when the plates ground together, subduction ceased, and any magma formation activity stopped, but you've got a slab being pulled down there. Okay, a few more little things then. So this is a nice diagram showing you the strata underground strata, rock strata, and here is a low angle thrust fault. Remember, this is with compression, so over time the thrust that this rock is going to be thrusted over and sit on top of the other block. And this is how, when you have lots of these thrust faults, you get slices and slices building up. And that's my next video. And final video is a lovely bit of 4x2, they call this in the building trade, which I had in my shed. Got the saw out, chopped it up, but I made sure that my fault planes had different angles, just because I thought I wanted you to realize that it's not always the same angle. These are probably quite steep. I think thrust faults are probably a much lower angle, much more horizontal, but you get the idea. So let's try to see if we can get this to work. Might have to wait a little while, and this is not looped, so this is a one-time only, but you can rewind this. I'm just waiting now. Here we go. So we've got compression. I'm shaking it, there's the earthquakes, but look at how those slices of lithosphere are gradually piling up over each other. It's very complex, very messy, but look at that. It was horizontal, and now I've got a massive pile, and that is like a mountain range. So that is how landscapes are formed by earthquakes. Now, talking of landscapes, let's have a look at some. So here's the process here. This is basically the formation of the Himalayas. We're talking back in time, well, 71 million years ago. Now, you might remember from that Phil Heron PowerPoint, you might remember that India used to be connected to Antarctica right down somewhere near the South Pole, and then it raced up and smashed into Asia. We're making it sound like it's a car crash. It's basically a car crash which has taken 70 million years. It's a very, very slow process. So here's India today having smashed into Asia and forming a mountain range called the Himalayas. If you do look at a cross section through here, this is basically before. I'm not sure when this was, but at some point, maybe this is just as India is here. I think this is basically when they're just meeting. Indian plate seems to have gone down here. The tip of the Indian plate has been smashed up. So as there's been collision, this bit here has been smashed up by compressional forces, and that's formed your lovely low angle thrust faults. And then as India, it's called a subcontinent because it's sort of small, continental crust. Anyway, they call it the subcontinent. So as the Indian subcontinent collided, then these thrust faults got pushed up over each other. See how they've been rising up over it and sitting on each other. Somehow that point down there has gone up there. It was down underneath somewhere deep down, and now it's high up. So the whole thing is basically slices building on each other, just like in the video. If you want to see it again, just go back and replay the video. So let's have a quick look at the atlas pages to get a real nice geographical context to this. So here's India. We've got the country of Nepal, and Mount Everest sits just about here on the border between Nepal and China. This is classed as South Asia. South Asia is really Pakistan, India, Nepal, Bangladesh, Burma. And remember, back in the colonial times, the British called this India. India was once from there, Pakistan, all the way to Burma down here. And don't forget, we also have Malaysia and Singapore. So we had a huge empire, obviously now independent, quite a long time ago. But this is a physical map. You can now see the rivers and the mountain features. One thing to have a look at is the key. This colour here, it's sort of purplish, but hasn't really come out too well, is land, very high elevation land. We're talking about more than 4,000 meters. And the plateau of Tibet is formed by the thrust faulting. It's not just the Himalayas, but this entire area here has been formed by slices of the lithosphere piling on top of each other and rising up to a huge plateau, which is the highest plateau on Earth. And it's been formed by the thrust faulting process, which I showed you through my little blocks in my garden patio. I zoom in here. This is the South Asia map. The colours have come out a bit better here. You can see this is Bangladesh on a floodplain where you've got the Ganges River meeting with the Brahmaputra River and forming the Ganges Delta. Here's the Bay of Bengal. India's on the left. Burma, which we call Myanmar, is on the east. And then this is Bhutan. This place here, the Meghalaya, incidentally, is the place with the wettest place on Earth during the monsoon season. So Nepal here, and if you look carefully, you can just about see Mount Everest, which is just there. 8,848 meters of elevation above sea level is very high, but really that's the edge of this huge purple area, which is the plateau of Tibet. It's a very, very cold, inhospitable place. It's got a very low population density, and it was all formed by the slices of lithosphere piling on top of each other through thrust faulting and compressional stress. A few extra things I've got here on the on this map. This is a seismic hazard map, I guess a seismic risk map. It's quite cool. You've got sadly Japan at high risk, the Philippines at high risk, and then this is called the Alpide Belt. It goes all the way through South Asia and Southern Europe. Greece, Turkey have lots of earthquakes, which formed those escarpments we saw used for those temples in ancient Greece. This is Iran, around here as well, and Iran has a history of lots of earthquakes, and it's quite a hazardous location. And this is the Himalayas, but carefully, this is where the collisions happen. This is the convergent plate boundary, but if you look at this, you've got earthquakes happening like 1,000, 2,000 kilometers north of the plate boundary. So I've got here, earthquakes are felt far away from the collision plate boundary, as that compressional stress, it's actually transferred to the entire system of thrust faults. There must be thousands of faults, and each time there's a movement, it increases force and the stress on other parts of the whole system. So this is the last few slides really. This is showing the Tibetan Plateau. These mountain ranges are being formed, as you might have heard. Mount Everest is rising. It's actually growing taller and taller. And that's because as India continues to collide into Asia and those slices of lithosphere are pushing over each other, it's actually lifting up Mount Everest. There's been two large earthquakes recently. Well, I say recently in this century. Sichuan earthquake here in China, 2008. That was a large magnitude of 8 on the moment magnitude scale. There was actually 2 earthquakes there, so it's quite a dangerous place. That's in China. And then Nepal, 5 years ago, had a large magnitude 7 on the moment magnitude scale. And that was a very, very large earthquake, which is one of the case studies we'll have a look at. And all these earthquakes, whether they are in China or whether they are in Nepal, are all formed by the collision between India and Eurasia. Sorry, India and Asia. Actually, it's India and Eurasia, isn't it? Now, up here, there's the Himalaya mountains. Up here, this is called the Karakoram Mountains, and this is in northern Pakistan. There's some great pictures. This is from the Karakoram Himalaya range. This is actually called the Karakoram Highway, built in 1979. I love this picture. These mountains are basically, they're very, very steep because they've been weathered by freeze-thaw weathering. They've been eroded by glaciers, and they have been basically slowly weathered and eroded to form these jagged peaks. I just love this picture. I just put it here because I just like it. Here's some crazy, absolute crazy bridge. But for some reason, they didn't build the bridge over the top of the thing. They built the bridge that goes through here and then goes through here. It goes through a hole in that river valley. I mean, I don't think I'd like to drive across that in a hurry, I tell you that. This also is a particularly worrying photograph. This is the highway. And yes, coaches are going to go under that little notch around here. Somehow there's a traffic jam here. Maybe they're having a little lunch break in the shadow of the rock. But I hope nobody just wanders off and falls over that edge there, because it's a long way down.